Hi guys, hold on. Okay, where am I? Let's just get a chart up so I can see what you guys want to go through. So, yeah, hi guys. Okay, so going to go through mainly AQA topics today. So, but they obviously cover a lot of the other exam board stuff as well. So, for physics tomorrow, what any suggestions of any things people want to go through? So I'm flicking about. All right, Half-Life. Let's start with a bit of Half-Life then. Okay, does anybody know about? You guys have got a nice break after physics, so you just got one more exam and then you got like a nice week off, so which is all good. All right. Does anyone know the definition of half-life? You could be asked for the definition. It can be a 1 marker or a 2 marker sometimes. Yeah, we'll go through circuits as well. Yeah. Alpha, beta, all of that. Yeah. Cool. Yeah. So, anyone know the definition of half-life? It starts off with the time taken. So you got the time taken. Is the time taken for half the isotopes. Now, there's a load of different ways you can say this in a sample to decay. So the time taken for half the isotopes in a sample to decay. I think if there's some people on the who can't chat yet on the chat, I think you have to subscribe before it lets you chat. Um, yeah, the number of radioactive nuclei in an isotope to half, but you always want to start with the time taken. So the half-life is the time taken for, you can say the radioactivity to half, the activity to half, or the radioactivity of a sample to half, or the time taken for half the nuclei in a sample to decay, or isotopes or atoms. They're all equally good. Okay, so let me give you guys a question. Whoa, boy, some long ass question. Okay, so if you've got a substance with a half-life of 10 days and a starting activity of 4,000, what will be the half-life after 40 days? So, let me work through this one and then I'll give you guys another one. So what you've got to do with this, you've got to start off at 4,000. You write 4,000. And then we also make sure you bring your highlighter because we can highlight in the question. We've got substance X, half-life is 10 days, starting activity is 4,000, and then what is it after 40 days? So what you're going to do is half it to 2,000. Now that is what happens when one half-life passes. The activity, by the way, we measure radiation in BQ becquerels. 1 becquerel means one atom decays and releases its radiation every second. So 4,000 becquerels mean 4,000 atoms are decaying a second. But after this amount of time, the radioactivity is decreased. So after 10 days, it's gone down to 2,000. Then after another 10 days, what's it going to be? It's going to be 1,000. So we got 20 more days to go. So you go from 1,000 to 500. And that's another 10 days. Remember, the total is 40 days. And then you just half it again to 250. So the answer, you might think this is seriously long writing this out. There's a reason why there's a reason why the whole of physics, yeah. Well, maybe. There's a reason why I do the long version and draw this out like this. It's because if you do it in your head and you go, right, it takes 10 days and 40 days, that's 4 half-lives. So you might go 4,000, 2,000, 1,500. Oh, it's 500. If you write it out, it's actually only halved 4 times. Each arrow is the dividing. So as long, or you could put 4,000 in your calculator and just press divide by 2 4 times. How do we know 4 times? Well, it said 40 days and it's halving every 10, so that's 4 divisions. However, it's easier to just write it out. So the answer would be 250 becquerels. Yeah, you don't need to know about antibodies for this one. Nah, nothing on antibodies. Right, let me give you another one. There isn't really a set equation for this. It's best not to have a set equation. Another question, let me see if you guys can do this one. Okay, so Sugar Ray Leonard, right. It's a bit. If a substance, let's not do a substance, has an activity of 200 becquerels. So becquerels is how we measure radioactivity. So that means 200 atoms per second are breaking down. Now, so, and rather than me say a substance, let me put this up here, because this is, if radon 235 has an activity, because I need to make it hard like it is in the exam. So if radon 235 has an activity of 200 becquerels, after 10 days, its activity is 25 becquerels. What is the half-life? Don't worry, I'm only spending a little bit of time on half-life. I'll do the graph after as well. Scalar and vector quantities come up in Physics Paper 1 if you're studying Edexcel or OCR. You'll be doing scalar and vector quantities. If you're studying AQA, that's coming up in Paper 2 under forces. Okay guys, how do you work this out? Really important, when you're looking at radioactive substances, don't pay attention to this in a half-life equation or when you're doing a half-life calculation. That's not of importance. That's just the name, radon 235 or thorium 236. That's just the name that differentiates it from other isotopes. That's not something we include in the calculation. So all you do here, start at 200 BQ. You don't need to write BQ, that's just me being long, and half it to 100. What's next? What are we halving it to next? We're going to half it to 50, and then we're going to half it to 25. I think I've made this a little bit awkward. So 200 to 100 to 50 to 25. How many halvings has that been? It looks like 4, but how many halvings has it actually undergone there? So remember I said that took 10 days. That whole thing took 10 days. How much is each halving worth? Well, there's 3 half-lives. So we've got 3 half-lives over 10 days. So we're going to do, you could do 10 divided by 3, and it's going to be 3.3 days. So the half-life is 3.3 days. Each time is taking 3.3 days. So it takes 3.3 days to half. Okay. Now, next, you could be given a half-life graph. So you guys might get a half-life graph if you're lucky. It'll say something like 8,000. Now they could say this is activity or becquerels. So there's the activity. Here's 0. And along the bottom of a half-life graph will be time. And this could be days, it could be years, it could be whatever. Okay. So, this is what a half-life graph looks like. It never reaches 0. If you keep pressing divide by 2 on your calculator, you can never get to 0. So, whatever number you put in, mathematically, if you keep halving any number, you'll never get to 0. So half-life on a graph should never touch 0. So notice why, that's why down here, it's not on, it doesn't eventually ever get to 0. So, how do I find the half-life on the graph? Does anyone know? With someone, Sophie asked, how did you know for this one how many times to half? It told us it was 200 at the start, the activity, okay, Sophie, and then it said after 10 days the activity is 25. So we can just keep halving from the first activity, which is 200, until we get to 25. So that's what we did there. We just started at 200. We said, okay, it's going to end up at 25. I'm just going to keep pressing half on my calculator until I get to 25, and then add up how many times did I divide, and that's the number of half-lives. Then you can work out how many days each one is. Right, guys, on one of these half-life graphs, you start at the top here at 8,000, okay? You're going to half, if it says use this graph to find the half-life, just drop straight half the activity over here, 8,000 to 4,000, draw a line straight across, straight down, and just read off the time. So this is like 0.8 years, the half-life on this graph. That would be the half-life. Okay, so that's all you need to do. You half the number on the activity, draw a line to the curve, straight down, and that's the half-life. Right, yeah, that's absolutely right, Natalie. You just read off at half. Right, what I'm going to do, people are talking about alpha, beta, and gamma. Let me quickly whip through alpha, beta, and gamma. So, yikes. There's alpha. Alpha particles are slightly positive. You don't really need to know that, so don't worry about that. They have, we can write 4 and 2. Now, some people like to write alpha like this, H and E, just to confuse you. So watch out for that. They might give you HE in the exam with a 4 and 2. Both of those are alpha particles. They're just different ways of representing it. What does this number 4 tell you? Well, what does that mass number tell you? You should know from chemistry. What does the mass number tell you? So I'm just going to go through alpha first, and then we'll go do beta and gamma. Anyone know what the mass number tells you? Protons and neutrons, Georgette. So the top number tells you the protons and neutrons. So alpha particles have 2 neutrons and 2 protons. So they're made of 2 protons and 2 neutrons. Okay, because of this, they're heavy. Okay, they're heavier than all the other particles. So they are the most ionizing. And this means cancer causing. So they're more likely to cause cancer, more likely to knock electrons off of other atoms, which can lead to a mutation in your DNA and cancer. So they are most ionizing. Don't really need to think of it as cancer causing, but ionization can cause cancer. However, because they're heavy, oh, Sugar Ray Leonard. Now, when I say they're heavy, they're incredibly light, okay? But compared to the other types of nuclear radiation, they're heavy. So because they are heavy, they are slow and have low penetration. I might make some spelling mistakes, just allow it because we just want to speed through. And range. So what do I mean by penetration and range? Anyone know what we mean by penetration and range? Yeah, Alice, BQ means becquerel, and it's the number of radioactive particles per second that are breaking down. So if this pen was radioactive and was made of 1,000,000 particles, if it had a becquerel, if it had an activity count of 2,000 becquerels, it means every second 2,000 of them are breaking down and releasing alpha, beta or gamma. So becquerels tells you how many particles are decaying per second, sometimes called the count rate. Okay, right, they're heavy and slow. Penetration and range is low. You do need to know alpha cannot penetrate skin or paper. So you can block alpha with a piece of paper, and it's really important to know it can't get through your skin. So we use radiation as something called radioactive tracers. This is where when someone's got a medical illness, we can give them a radioactive sample and it will release radiation. We can then take a piece of equipment, this is a calculator by the way, but it could be a radioactive detector called a Geiger-Müller tube that detects radiation, and we could move it around someone's body, and where it clicks we'd be able to tell where the radiation's coming out of their body. Okay, alpha would be useless, so you need to know that alpha is a rubbish tracer because it can't penetrate skin. So if someone swallows it, it can't get out, which means you can't detect it outside of their body. So alpha wouldn't be a useful radioactive tracer. It can't go through the skin. In fact, alpha is in my smoke alarm up there, and it's in, if you've got any fire alarms or smoke alarms in your house on the ceiling, there's alpha radiation in them. Okay, it's not harmful to you because it can't penetrate your skin, so it can't get into you and cause you cancer, even though it could be the most dangerous. If you swallowed your smoke alarm, if you got hungry and ate your smoke alarm, then you're screwed because you'd be contaminated with alpha and it would go around ionizing all the cells in your body and give you cancer. But from the outside, it ain't getting in. It's not going through your skin. Okay. Alpha does damage cells. It does damage cells, but it can't get through your skin because it's not penetrative enough. Inside the body, that would be seriously dangerous, yeah. But more important, it's not useful because it can't get out, so it can't be detected outside the body. So that's alpha. Right, let's look at the... oh, sugar. Let's look at the nuclear equation for alpha. You'd need to know the nuclear equation for alpha. So I'm just making this up, but if I had isotope X and it had a mass number of 200 and an atomic number or proton number of 100, an isotope X, when it decays, becomes isotope... I was going to say Y, but then I'm not going to say Y. When it decays, it becomes isotope Z plus alpha. The numbers for alpha are 4 and 2. What would be my missing numbers here and here? Can anybody work out what the missing numbers are? This is called a nuclear equation, and this is for alpha decay. So anyone work out what the missing numbers are? Yeah, Sophie, so alpha damages cells by knocking electrons off of atoms within your cells, and technically, yeah, by doing that. But alpha isn't going to be able to get through your skin to damage your cells, so you don't have to worry about alpha from outside. It's harmless to you outside. Yeah, that's right. It's well done, Alice. It's going to be 198. Oops, Sugar Ray Leonard. Put the wrong thing there. It's going to drop 4 from the top and be 196. Painful watching me rub this crap out. I mean this stuff out. So it's going to be 196 and it's going to be 98. Okay. Now they could ask you that. They could do this. Watch out for this as well, guys. They could do this. And they could be like, okay, what type of radiation? Fill out the boxes, 3 marks. What type of radiation has come off? And you'll be like, oh, it's lost 4. So it's lost 4 there. Oh, it's lost 2. It's gone from 100 to 98. It's alpha. So that's called a nuclear equation. Let's look at the next one, okay? Yeah, we haven't done beta and gamma yet. We're going to do beta and gamma now. So let's go with... Beta's the hardest one to know what it's made up of, and gamma's the easiest. Gamma's a piece of P, so you ain't got to worry about gamma. Alpha, a bit easier than beta. So beta, again, just to be a pain in the butt, beta has 2 symbols, just like alpha could be He for helium. Beta is an electron, and it has the number 0 and -1. Some people and some exam boards, and depending on how much they want to irritate you, they use the beta symbol with the B. So it could be an E with a 0 and a -1, or a 0 and a -1 with a kind of B for beta symbol, a slightly funky B. I think it's a Greek B. Okay, that's beta. But what is beta? You know that alpha is 2 protons, 2 neutrons that have been fired out of the nucleus of an atom when it decays. This is the difficult bit with beta, okay? Beta is an electron that is emitted from the nucleus during decay of an atom. So, why is that unusual? Why is that weird? Anyone tell me why that's weird, that statement? What's strange about it? Beta is an electron that is emitted from the nucleus during decay. Anyone know why that's a bit weird? Yeah, very good. No electrons in the nucleus. Yeah, electrons don't come from the nucleus. Absolutely, well spotted. But beta does. So how is that working out? I'll show you how that's working out. What happens is a neutron splits into a proton. This is all inside the nucleus when the atom's a bit unstable, and it splits into an electron. And the electron is fired out of the nucleus. So imagine these guys are in the nucleus. So there's no electrons in the nucleus normally, but with beta decay, a neutron breaks in half, leaves behind a proton, and the electron fires out. So let's look at some of the things about beta before we do the nuclear equation, which will explain all of that. So beta is less ionizing than alpha. Okay, so it's less likely to damage your cells, but beta's more dangerous because beta can get through your skin. Okay, so it's less ionizing than alpha, but more penetrating. Oh my gosh, I'm just going to allow the spelling, right? And more range. So it can travel further before it's absorbed. Oh, geez, Louise. All right, let's just leave it at that with the old spelling. You do need to know what beta's stopped by. Beta is stopped by thick aluminium foil. So it's still pretty thin. It will go through paper. It will go through thin aluminium foil you wrap your sandwiches in, but slightly thick, better quality aluminium foil, it will get stopped by. So still quite easy to stop. Yeah, don't worry about the exam. You're going to get through it, so it's going to be all right. Okay. Right. So, beta decay, less ionizing than alpha, but more penetrating and more range. Beta is stopped by thick aluminium foil. Now, here's the nuclear equation for beta. And this is going to explain some stuff for you guys. So, there is an atom called carbon-14. It's a radioactive atom. It's unstable, and we'll talk about why it's unstable. Yeah, so beta is less ionizing, but can be more dangerous, Alice, because it could penetrate through your skin and get to some of the cells within your body, okay? So it's less ionizing, but it still can cause cancer. It can still knock electrons off of your atoms and turn them into positive ions, which can cause them to react. But it can penetrate further, yeah? It can get through my t-shirt. Alpha can't even get through this t-shirt, let alone my skin. Beta could get through the t-shirt maybe, and maybe through my skin and into my cells. Now, this is the nuclear equation for the decay of carbon-14. You don't need to know any of these off by heart, but you do need to be able to apply your knowledge to them. So, here is my beta particle, 0 and -1. Can anyone tell me what the two new numbers for the nitrogen formed from the decay of carbon-14 are? Oops. Okay, guys, if someone is spamming on the chat, you know you can just remove them. If you click on their name when you're watching the chat and you click remove, their comments will no longer appear on the chat. So if someone's irritating you or saying stupid things that you and you're just like, sometimes some people have already messed up and they haven't got it in them to focus and get down to work towards the exams, and their only hope of little bit of pleasure is to stop other people from getting success. So you might want to click on their name, click remove, and then they're not going to bother you anymore. So you might want to do that. Yeah, so well done. 14 and 7. A lot of people would put 5. This is a common mistake people make. They put 5. Don't do that. It's an equation. So everything on one side has to balance on the other side. Okay. Now, we talked about the beta decay when the neutron breaks into a proton and an electron, which is emitted from the nucleus. And this really explains, you can see here, some of the questions that have come up in the past is explain what happens in the nucleus of carbon-14 when it decays. So what happened in the nucleus? Let's look at 14 here. 14 means there was 6 protons, right? By the way, you don't write this on the equation. This is just me showing you. There's 6 protons and 8 neutrons. Okay, so 6 protons, 8 neutrons. When one of the neutrons breaks up over here, that means that's going to still be, well, it turns into a proton. So our protons go up to 7, but our neutrons have dropped to 7. So when I said beta decay is a little bit more complicated, the neutron breaks up, so it went from 8 neutrons, 6 protons to 7 neutrons, 7 protons. It gained a proton, lost a neutron, and chucked out an electron, and that's beta decay. You may be asked to explain what's happening in the nucleus during beta decay, and if that's the case, you're going to smash it because you're going to say, well, one neutron split into a proton and emitted an electron. The mass number didn't change, but the proton number did, okay, or atomic number did. Right, let's move on. Now, beta can be used as a radioactive tracer. So if I had something with beta and I was in the doctors, they might say, right, we want to check if there's a blockage in my intestines. They may give me some beta, and then they can use a special machine and find, oh, it's stopped, it's not moving down, there's a blockage there, and then they could operate on me. We call that a tracer. And they can detect beta outside my body. Better to use gamma, but they can use beta. Okay. Gamma has even more penetration. Now, gamma's the easiest of the lot, okay? So there's hardly anything to talk about with gamma. Gamma is in your paper 2. It's an electromagnetic wave. So it's in both papers 1 and 2. It's not a particle. So it's the same as light. So the whole E equals mc squared. Well, gamma radiation is light. Radio waves, microwaves, they're all light. Okay, they're all types of light. There's visible light, ultraviolet light, and we call those electromagnetic waves. Gamma is one of those. It just so happens that it comes out of decaying nuclei as well. So gamma is a wave. We say it has no mass. We give it this weird kind of Y symbol. We give it 0 mass and 0 charge, or 0. Both numbers are 0. So it won't affect, in a nuclear equation, if gamma's coming off, it won't change any of the numbers. It won't change the element at all. What do you need to know about gamma? Gamma is the most, it's the least ionizing and most penetrating. Okay, only stopped by thick lead. Okay, right. If there's a nuclear explosion, the alpha and beta aren't getting to you. They're getting blocked by the walls, your windows. They're getting blocked by the leaves on trees. They're getting blocked by your clothes. Gamma rays are going to get through the walls of your house and into you. But if you go into the underground station, you're fine, because there's a lot of metal and concrete and dirt. Really, it's going to get absorbed. So gamma gets stopped by thick lead. Gamma is the weakest at ionizing, however, probably the most dangerous, because it can go through us and damage a lot of our cells on the way through. It's a good radioactive tracer because you can detect it outside the body. So if someone swallows it, you can detect it outside their body. If you were designing a radioactive tracer, a medical tracer, you want a short half-life and good penetration, so it can be detected outside the body. Okay, so if you were designing a radioactive tracer, gamma's a good one. You want a short half-life though, not seconds. The doctor's going to feed you some radiation and say sit over there for 2 hours, and then we'll get the machine ready and put you under it. So maybe a half-life of 8 hours, 10 hours, 12 hours. So the radiation becomes harmless very quickly. It's halving in its it's decaying very quickly, and in a day or two it will be completely harmless within your body, or it will minimize the harm. But it needs to be detected outside your body by the machinery, so it needs to be gamma or beta. Okay, a medical tracer is a medical tracer is a pill or something that contains radioactive isotopes, unstable isotopes that will release radiation, and they can be used to trace things around your body, hence the name trace, and find certain things, and like we can detect them when they're in certain things. That's a really good point, Rod. How does gamma make the nucleus more stable if it doesn't have mass, if the nucleus doesn't lose protons? What they don't teach us at this GCSE level is that E equals mc squared. So yeah, gamma may just be energy, but that accounts for a little bit of mass, but that's on a higher level and a different model. You don't need to worry about that. But yeah, technically, when gamma comes out of the nucleus, it is becoming more stable because it is losing mass. There's not just protons, neutrons, and electrons in a nucleus. There's like, I don't know, 16 different particles. So there's loads of other stuff in there. So don't worry too much about that. You won't be tested on that. Someone mentioned chemo, like chemotherapy. Yes, gamma chemotherapy is really slightly different, but radiotherapy, radiology, is when we use like radiation, basically. And what you would do with gamma, if just to show you what you would do with cancer, if this was a patient, oh my gosh, they've got a long neck, and they had brain cancer here. Now, gamma, it's risk versus reward. Gamma radiation is going to damage some of their healthy cells and potentially cause cancer. But what we can do, we can also use it to fight cancer. We're going to fire a weak ray of gamma, very low intensity, hopefully not to damage any of those healthy cells. But what we're going to do is hit it from every angle. So on the way through, these healthy cells here are not hopefully getting damaged, ionized, and turned into cancers themselves. But where we're concentrating the gamma rays, we're going to ionize and destroy that tumor. Okay, so where they come together will be very complicated. So this is why people who are doing this and using these machines need good math skills, and you need to have all those qualifications if you want to be someone who's going to be destroying brain tumors and stuff like that, because you need to get the maths right. You're going to get all these rays going in and minimize the damage to the patient's healthy cells. Right, that's gamma radiation. Gamma radiation, what else do we need to know? Let's zing, because we're spending a bit too long on gamma, beta, and alpha. Now, you guys need to know contamination. Let me just zing, and then we'll get off of this topic because this is only a quarter of the course. Contamination versus irradiation might come up. So what is contamination and what is irradiation? Yeah, I'll do specific latent heat. X-rays is, it depends if you're doing AQA or not. So depends which exam board you're doing. X-rays generally, okay, X-rays are very similar to gamma rays. They're pretty much the same thing, but they're just before gamma rays in the electromagnetic spectrum. But X-rays, yeah, X-rays have a longer wavelength. They're not as damaging as gamma rays, not as penetrating. They're absorbed by your bones, hence why they can show your bones. But you don't need to do that until you're doing waves and radiation, which is a slightly different topic. Okay, contamination versus irradiation. Contamination is worse. They're both bad. What do you need to know about them? Right, here's my radioactive bit of alpha. It's inside this object, and it is ionizing all the cells in this object. So if I got radiation under my, oh, no, sorry, not swearing. If I got radiation under my fingernails, if I got some sample under there, I'd be contaminated. If I got it in my hair, if I swallowed it, once it's inside me, I'm contaminated. If a radioactive sample is dropped in this cup, it's contaminated. It means that wherever you take that object, wherever I walk, I'm giving off radiation and I'm radiating everyone around me. Irradiation is something slightly different. Irradiation is when radioactive particles pass through an object. And any of you that have ever broken your arm and ever had an X-ray, or at the dentist, you've bitten on that thing and the dentist goes out the room and they fire an X-ray, you're being irradiated right there. And that is, the radiation is passing through you, and on its way through, it may ionize one of your cells and you may develop cancer, but it's like a 1 in a million chance, and it's more important to get your teeth right or check that you haven't got a broken bone, because it's such a small chance of you developing cancer or getting damage from the X-rays. That is irradiation. It passes through you. It's still dangerous. We can protect against that by leaving the room. Notice the dentist or doctor always leave the room when you are being X-rayed. They go out the room. Okay. They can stand behind a lead shield. You can wear lead clothing. You can wear a lead apron like that, and it will protect them from irradiation, from the radiation going through them. Contamination is different. If you want to be protected against contamination, you need to wear gloves. That's not going to protect you against being irradiated. Radiation, gamma rays can go through gloves, right? They can go through a mask. But I'm saying I don't want to breathe in any particles that are going to give off radiation for the rest of my life, which might be very short, might live a week or something, while all my cells get ionized. So to protect against contamination, you want to wear gloves, use tongs to pick up any radioactive material, wear a breathing mask to protect you from breathing in any radioactive particles. Irradiation is different. You're just protecting from the radiation going through you. Okay, like for instance, when you put your tea in the microwave, who does that? When you put your food in the microwave, it's getting irradiated. Microwaves are going through it. Is it dangerous when you take it out and you drink it? No, there's no radiation in it. It's gone through, come out the other side and gone. Okay, that is not dangerous. So we can irradiate stuff. We use gamma to sterilize medical equipment. That's something I didn't explain. If you've got medical equipment and you've just been doing a heart operation, we fire gamma rays to kill any bacteria. We've irradiated the equipment. The equipment is no longer dangerous. It's not contaminated. It doesn't have anything in it that's giving out gamma. All right, enough of my waffle about contamination and irradiation. We need to get on. Let's... circuits, potential difference. Radiotherapy, yeah, absolutely, yeah, is a use of irradiation, yeah. Radiotherapy is like when I drew that little picture, you fire the gamma rays into someone's body to destroy a cancer. That would be radiotherapy. Chemo suggests chemicals. You give someone radioactive chemicals and they go somewhere and destroy it like that. So that's a medicine-based one, I believe, but I'm no expert on chemo and radio. People are saying circuits a lot, so people want to get down with the circuits. Let's have a look at circuits and national grid. Yeah, okay. Let's do a bit of... Actually, I might have a slide on here. Bit of national grid somewhere. Okay, let's get down with some electricity. There might be some other questions you've got on radiation, but I'll just waffle on forever, unfortunately. Right, you've got the national grids. So this won't take 5 minutes, what you need to know about the national grid. Okay, when we produce electricity at a factory, like a power station, I don't know the exact number, maybe it's 25 kilovolts. Now, what is 25 kilovolts in volts? In physics, you need to convert kilovolts to volts because we use potential difference, we use voltage, not kilovoltage. So, anyone know how many volts are in 25 kilovolts? Yep, well done, 25,000. Sounds like a lot, it is. That's enough to kill 20 elephants, right? It's a lot of voltage. We want to step it up and make it even more. So we have a step-up transformer over here. This is a step-up transformer. What does this do? This increases voltage. How does it do this? It has more turns on the secondary coil than primary coil. Believe it or not, they probably won't ask you this because this is more of paper 2, but it is written in the syllabus for paper 1 as well. So that's how it works. The voltage comes out higher. We actually step the voltage up to something along the lines of 400 kilovolts, 400,000 volts, right? You may be asked why we're going to use 400,000 volts. Why step the voltage up? 25,000 is a lot of volts. Why make it even higher for transmission? Transmission means for transport. So about 20 miles from your house is a power station. We're going to send the voltage through the wires to your house at an incredibly high voltage. We're going to step it down when we get to your house to make it safe, but the question you could be asked is, and does anyone know, why do we use high voltage for transmission? So you need to be able to answer the question, why we use a high voltage for transmission. Potential difference, really good. Potential difference is voltage, so we're increasing the potential difference or increasing the voltage. Yes, Sophie, it's more efficient. What do we mean by more efficient? Very nice. Lowers the current. Well, so what you really want to say is, if you look at this equation, and this is on your equation sheet, P equals I times V, right? Power, I stands for current, by the way. Power equals current times potential difference or voltage. Absolutely, less wasted energy, less energy loss. Really good. Reduces thermal energy loss is good. You'll probably get most of the marks just saying, so we can have a low current, less energy losses. But if you wanted to understand why, which you don't really need to, but if you wanted to understand why, as the power station, it says it in the name, power station. We want to deliver power to the consumer, to you in your house right now. So you can be on this live, so you can have your lights on, so you can watch TV, so you can be on charge your phone and all of that. We need to deliver power to your house. Now we can deliver that as current and voltage, because power is equal to current times voltage. There's a problem. High current wastes a lot of energy as thermal energy, oh gosh, to the environment. I'm writing too much really. So high current wastes a lot of thermal energy to the environment, so I don't have to use a high current. I need a high current when I get to your house so you can use all your gadgets, but on the way there we can go, hey, let's use a low current and a seriously high voltage, because if my current is 1 amp and my voltage is 400,000 volts, I'm still delivering to your house or to your street 400,000 watts of power. So essentially it's just being a clever way to deliver power to your house using a low current. So if you're asked, cutting all the ball, if you're asked why do we use a high voltage for transmission, it's to reduce energy losses, and so we can deliver power with a low current. Now when we get to your house over here, when we get to your house, we need to step down the voltage to, does anyone know the voltage of the mains? Oh my good gosh, I think I've lost. Connection says it's all right. Okay, nice. We've got a bit of buffer in there. Lost everybody for a second. Yeah, well done, guys. It's 230 volts. So, 230 volts. Nice. So, we step it down to 230 volts. You could be asked why, and that's for safety, to avoid electric shock. 400,000 volts is a lot. What's going to happen to the current when we lower the voltage? I'm delivering this. What's going to happen to the current? Current's going to increase. So when we lower the voltage, the current will go up, and then we can deliver current safely to people. But yeah, essentially we want a low current to reduce energy losses, and that is the national grid. You may be asked, what is the national grid? You want to say two things. It's a series of transformers and cables that deliver power from the power station to the consumer or to houses. Okay. Yeah, so current will increase when the voltage goes down. That's right. It's current that makes your mobile phone hot when you're charging it or when you're on it. It's current that makes your laptop hot. It's current that makes any electrical appliance hot. Current creates heat because the electrons collide together. Current is the flow or the rate of flow of charge, and the electrons rub together, releasing heat. Okay. Now people said they wanted let's do a bit of circuits. Let's do some circuits. Disgusting circuits. Oh, that's a bit hideous. Do I really want to go? Alright. Let's do a few circuits questions, guys. Okay, guys. Have a go. Give yourself a minute. Have a go at these nice little warm-up ones. Which of these components is a variable resistor? Which component is a thermistor? In which component will the resistance decrease when the temperature increases? And in which component will the resistance decrease when the light intensity increases? So Frank, are you going for A for the first one? The variable resistor is A. You are spot on, Frank. Yep, that's the variable resistor. Now, on variable resistors, just in case you don't know what they do, if you're asked what a variable resistor does, you obviously want to say it changes the resistance. It's actually used to change the current. Resistance and current have an inverse relationship. When resistance is high, current is low. So if you've got a dimmer switch in your bedroom, turn down the lights. When you turn up your volume, right now, see, I'm going to change my volume on my volume control. That is a variable resistor. By changing my volume, increasing or decreasing the volume, I'm changing the resistance and therefore changing the current. So that's what a variable resistor is for. It's actually for changing current. Which component is a thermistor? Anyone know what a thermistor is? All right. I don't know what AC, but yeah, AC is right. Yeah. C for the second one. Nice. That's the thermistor. What are thermistors for? You've got them in your fridge. Anything where you want to control temperature. Notice the similarities of rectangle. That rectangle means it's something to do with resistance, as well as it says istor. And which component? Yeah, it's the thermistor. So we're looking at A, C, C. Which component? Blah, 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 B. Right. And this is the light dependent resistor. Now, there are two graphs for these that you need to know. These sketches kind of off by heart. So we've got temperature here with a T, and this is my symbol for resistance, which is ohms, the omega symbol. And hold on, let me just check, am I drawing where my face is? No, not yet. Okay, so you need to know the relationship with a thermistor. As resistance, as the temperature increases, resistance decreases. Think about your fridge. When you leave the fridge door open, what happens? It goes beep, 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 and it gives you, you've all left your freezer door or fridge door open in the kitchen when you've grabbed something, and it starts beeping to tell you you've left it open. It's not a clever machine. It's got a thermistor in there in the circuit board, and when the heat increases, the resistance in that circuit decreases, allowing the current to flow in the circuit and the alarm to sound. So putting thermistors in, they're in what we call sensing circuits, like sensitive circuits, so they can sense changes in the environment. The other one that you need to know is this one, the LDR, the light dependent resistor. Think of those two arrows as rays of light hitting a resistor, and it has the exact same shape graph like that, and the resistance goes down when it gets more light. How many of you have got a Ring camera? Okay, you might have a Ring on your doorbell. Someone comes to the door, you get a little text message on your phone, or the camera switches on and starts recording them. Essentially, the light from their body lowers the resistance in the circuits in the camera, allowing the current to flow in the recording circuit, and the camera will switch on and start recording the moment it sees something. Some of you have got security lights outside your house, and when a cat walks past at night, the light comes on in your garden. And again, there is an LDR, a light dependent resistor in there, a sensing circuit. As the light from the cat's body hits the resistor, it lowers the resistance and allows current to flow and the circuit to switch on and start recording, or the light to come on, or whatever it is. So there's sensing circuits. Right. Okay. Another simple one. We've got two arrangements. Two are in series, two are in parallel. Describe the difference between a series and parallel arrangement. Okay. Which arrangement has a resistance of 10 ohms? Which arrangement here has the highest resistance? Okay. Does anyone know which of these four circuits has the highest resistance? Yeah, if we look at P, in a series circuit, you add them together, so we got a total of 20 ohms. In series circuits, you add them together. R is 10 ohms. Now we get something weird happening in a parallel circuit. It can be explained using the equations, but we don't want to go too deep on an explanation for that. But essentially, when you add these together, the total resistance in a parallel circuit, you need to know this, the total resistance in a parallel circuit is lower than the smallest resistor in the circuit. So this is going to be 9 ohms. It could be 6 ohms, it could be 5 ohms, but it's lower than 10. Here, when I combine these two, 5 and 5, I get 4 ohms or less. So parallel circuits, total resistance is lower than the smallest resistor in that circuit. Whereas with series circuits, you just add them together. Shit, what is happening here? Ooh, it keeps buffering out there. Okay. All right, guys. Are you still with me, or is it? It seemed to be like mashing out there a little bit. All right, let's move on. Okay, nice one. Cool. Right, here's a really hard one. So just going, before we do this hard one, we're just going back here, guys. This is the weird thing. When you're in a parallel circuit, the resistance gets lower the more resistors you add. And this is great news, because look at my light bulbs on my ceiling. They're nice and bright. As I add more lights, they're technically like resistors. They have resistance. As I add more lights, it's going to get brighter. So parallel circuits are awesome because you lower the total resistance of the circuit the more things you add. So you get more current with a lower total resistance. Now let's zing on. This is a difficult question. It says the lamp. So let's go through this question. The lamp shows a circuit that a student built. The lamp has a resistance of 10 ohms. Okay. Each resistor has a resistance of 10 ohms. So what I'm going to do, I'm going to graffiti up this and write, okay, that's 10. That's 10. And they told me that the lamp is 10 as well. And we're talking ohms. So we're talking not amps or anything. We're talking like the little upside down horseshoe, which is the symbol for resistance. It says, what is the total resistance of this circuit? What do you reckon? Now, this is a weird one because we've got a parallel part to the circuit and a series part. So in series, you add them together to get the total resistance. When it's parallel, they're lower than the lowest resistor in that part. So what do you think the total resistance is of this circuit? Is it between 20 and 30? Exactly 20, exactly 30, or less than 20? Let me give you a few seconds to think about that. Okay, yeah, so what we do here is we go, okay, this is parallel. Maximum resistance for this is 9.9 or something. So that, when we add those two together, it's going to be like 9 ohms. It might be 8, it might be 6, it might be 5. We'd have to do a calculation to find it out, which you don't need to know how to do. And then this is 10 ohms. So I'm going to do 10 plus 9 because the parallel part is in series to the light bulb. So it's 10 plus 9. It's going to be less than 20. I can't tell you it's 19 because we don't know exactly, but it's less than 20. So that's a little bit of a difficult question. Yeah, less than 20. But don't worry, it's a hard question. And then it says explain your part to A. So you just say that the two 10 ohm resistors are in parallel, so the total resistance is lower than 10. And you add this to the light bulb, which is 10. The student placed one of the resistors with a thermistor. This is the symbol for a thermistor. Can't really get you to draw it out on the chat. The student increased the temperature of the thermistor. Explain. This is a difficult question as well. So explain how the current in the thermistor changed. Okay, so they've changed one of the resistors into this, like that. They've made a thermistor. Explain how the current in the thermistor changed as the temperature increased. So when the temperature increases, yeah, so yeah, that's right. Well done. Yep, absolutely. Yeah. Well done, yeah. Temperature increases. So that's where you've got to know that sketch off by heart with the temperature going down as it goes up. So well done, guys. Good answers there. Yeah, resistance decreases, which means the current increases. Nice. Nice. What is this? I don't know if I want to do any more of these. Let's have a look. All right. Let's skip some questions for the moment. And let me get through a bit of the theory for those of you that want to. By the way, yeah, we talked about National Grid. Right. There are some disgusting practicals. Did I put anything on here? Let me have a look. One sec. Oh yeah, I did. Right, here's some practicals I want to go through for. This is a practical. Someone actually mentioned this earlier. I can't spell. Resistance, not that I can't spell. They mentioned resistance of a wire. There's 3 core practicals in the circuits topic. Yeah. Your core practicals, we've got density one, we've got specific heat capacity, and then there's like 3 electrical practicals. So there's like 5 core practicals: density, specific heat capacity, and then 3 electricity ones. So let's have a look at the first electricity one that could come up, but I can't tell you whether it's going to come up because I have no clue. It's the resistance of a wire. So what we're doing here, you're going to change the length of a wire. Okay, you kind of want to be able to set up a circuit like this, and what should be in these circles here? What meter should I put there, and what meter should I put there around my length of wire? What do you reckon, guys? What measuring things would I need to calculate resistance? Bearing in mind you're going to have V equals IR written on your equation sheet. So yeah, so the predictions for the practical, it's hard to say really. They love to ask density because it's nice and easy for them. Or specific heat capacity maybe. That's a difficult one, so we'll go through that in a second. Yeah. Well done, guys. V in para, amp in series, super duper duperless. Right, if I'm going to investigate the resistance of a wire, you need 5 lengths of wire. 5 lengths of wire. We're going to change the length. They may ask you to change thickness. In that case, keep the length the same. That is my independent variable, my IV. So then I'm going to be measuring current and voltage and then you're going to get marks in this practical for writing V equals IR and rearranging it to say resistance is voltage over current. Calculate the resistance for each length of wire. Repeat 3 times for each length of wire and work out the mean resistance for each length of wire. You're going to get marks for selecting the right equation. You're going to get marks for rearranging the equation. Marks for pointing out the independent variable, which is 5 different lengths of wire, and then you're going to get marks for your control variables. This is my dependent variable, by the way. Oh geez, that's the dependent variable. I don't know what's going on with my capitals. Your controls, what would I need to control? Well, if I'm changing length, thickness of wire, type of wire. Now they could give you a practical on any of these. They could say we're going to do silver, copper, gold, platinum. We're going to use 5 different metals. Then you've got to keep the length and the thickness the same of the wire. So really you'll get marks for just coming out with some of the control variables. One of the other things to do, yeah, specific heat capacity might have been last year, but you know what? They sometimes come 2 years in a row, so it's difficult. Remember, if you were doing combined science, I think they did the amylase practical again. 2022 was the amylase enzyme practical, and I think this year they've hit you guys again with it, I think. If what I heard is true, they hit you with the amylase enzyme practical again. So it's like, well, it's like electrolysis in chemistry. It's come up every year for the last 6 years. So not as a practical, but the topics come up. So just remember the control variables. And with this one, the wire's going to get hot. So you want to switch off. This is the thing with all electricity practicals. You can always just throw this in, whether it gets a mark or not. Switch off equipment, allow to cool down. Why? Not only is it a hazard because you could burn yourself, but heat increases resistance, which will change your current reading. So you need to know that. They might say, why, other than safety, why is it important to let the equipment cool down? Well, if it gets hotter, the resistance goes up, and this will change your reading on your ammeter. So it's going to make your results less accurate. All right, let's look at the other quick electrical practicals. Okay. Okay, so independent variable is whatever you're changing. The dependent variable is what they're measuring. So if they're saying, so whatever they change is the independent. Whatever you measure and you're recording is the dependent, and the control variables is anything that would affect the results. So here, this practical, for this prac, what we're doing is, oh geez. So this is really investigating current and voltage in different components, and there's 3 that you have to know off by heart. Who knows what symbol that is? Anyone know what that is? And I'll draw a circle around it. Anyone know what this symbol is? Yeah, diode, and this one is a resistor. So you have to know how to do this practical for any one of these, okay? Each of them gives you a slightly different graph, which I'm going to go through in a second. Let's go through the practical. Yeah. You guys have smashed it with the components. So this one is set up for a light bulb. Notice we need a variable resistor. That's the rectangle with the arrow through it. That is so you can change the current. I'm doing an IV practical. So if they mention IV or current and voltage, you want to investigate current and voltage, you need a variable resistor so you can do 5 different currents. So what we're going to do is set up circuit. By the way, in a 6-mark circuit practical, you'll get 3 marks from drawing the correct circuit setup. So, which is voltmeter in parallel, ammeter in series. Set up the circuit. Use variable resistor to change current. So you're going to change the current to 5 quantities, I don't know, change the current 5 times, whatever. You're going to do like 1 amp, 2 amp, 3 amp, 4 amp, 5 amp, whatever you want to do, okay? I don't know why my 4 is not working very well. My keyboard 4 got to smash it. Right, 1 amp, 2 amp, 3 amp, 4 amp, 5 amp. So you're going to change the current. That's your independent variable. You're changing the current. You're going to record the current. You might say, hey, but I'm changing it. But you still need to record it on your ammeter because due to resistance and things, your recording of your current may not be exactly what you set the variable resistor to. So record the current, record voltage, and oh, sugar, and plot an I on, yeah, and plot on IV graph. Now here comes the tricky bit. If you get this one, here comes the tricky bit. You're gonna reverse the battery and repeat. And this gives you negative readings, okay? So what do I mean by that? I've kind of like messed this bit up over here. So you're going to get 3 different readings. So let's not do that. So we were looking at a light bulb, and you're going to go, okay, here's IV. When I did it the first 5 readings, 1, 2, 3, 4, 5, I'm going to get a curve like that with a light bulb. When you reverse the reading and you switch the battery around, it's fine. All that does, it doesn't mess up your practical, it just gives you minus numbers, which I can plot on this half of the graph, and I'm going to get an identical copy, and that's why we get that shape, S-shape graph or sigmoid graph there. Okay, so that's 5 negative readings, 5. So this is the positive half. Then I flip the battery around, and I got 5 negative readings, and I plot them on there. And that's my IV graph. And they might ask you to explain why it curves off, and that's because filament lamps, what happens to filament lamps? They're not like all the lights you've got in your house now. Does anyone know what happens to filament lamps? These are the old-fashioned lamps we used to have in England like 20 years ago. Get hot. They heat up, and when they heat up, resistance increases, and that stops the current increasing. Okay, so they get hot. You can call this heating effect. It's due to the positive metal ions and electrons colliding, releasing heat, increases the resistance, makes it harder for current to flow. Okay, yeah, so they heat up, the heating effect. That's what causes that S shape where the voltage is still going up but the current's not going up anymore. Okay, you're going to get a different shape graph for each of these. So with the diode is going to look like this, okay? The diode's a strange one. The diode goes like that. When you reverse the battery, you're going to get no readings here in the negative. Does anyone know why we don't get any readings on the diode there? I've kind of not left myself with any room. Yeah, resistance always goes up when heat increases, yeah. Yeah. But why with the diode do we get no readings? Does anyone know why? We only get readings when the battery is in one direction. Very good, Claire. Yeah, it only allows current in one direction. Now the confusing bit, you see you've got this triangle on the diode right here. You've got this triangle and then a line. So what it's saying is current can't go that way, basically. Current's not allowed that way. We're blocking it. So when you turn the battery, it can't go. So it means you get no readings when you reverse the battery. Okay? Yep. And then you got the resistor. I think you're getting all the formulas on the equation sheet. I don't know whether you get efficiency. I think you're getting all the formulas. And when you get a resistor, if it's something called an ohmic resistor, you're just going to get a straight line when you reverse it. And an ohmic resistor, what doesn't it do that the filament lamp did? The resistance doesn't change with temperature. So an ohmic resistor is kind of like an ideal resistor or whatever. It's a wire basically. Yeah. Right. Wasting a lot of time. What the hell is that? Oh, that's just the resistance of a wire. Yeah, we did that. Oh, I know what I want to do. Let's just... Oh, there's one. There's one. There's one of your core pracs, guys. Here's a core prac. You've probably done this question before. 6 marks. Who's going to tell me... What's the... You can get it off your equation sheet. How are we going to find the density of that chess piece? How will you find the density of that? Anyone? Awesome, stuntman. It's D equals M divide mass over volume. You're going to get a mark for selecting it. Boom, from your equation sheet. Now we want to know, how will you measure the mass? Yeah, but you're going to have to say, I'll do the specific heat capacity one in a sec. How are you going to measure the mass? Anyone? How do you measure mass? Yeah, nice flat pan balance. Yeah, so measure mass, balance. You might want to say 0 scale first, or 0 the balance, whack it on, measure the mass. You've done the equation, you've done that, you've scored 2 marks. Now's the hard part. Someone said Eureka can. You'll get a mark for that, but you might... Eureka can's quite hard to explain. Because this is small, you can drop this in a measuring cylinder, right? And what you would do, let me show you how you drop it in a measure. I'll show you the 2 versions. So you can do either one, whatever one you prefer, okay? You can get just as much marks from saying measuring cylinder. Here's my measuring cylinder. And here's my water. I'm going to fill it with some water. And I'm going to fill it up to like 50 centimeters, let's say. Then you're going to chuck your chess piece in there. What's going to happen to the water when my chess piece, when that goes in? So we're going to chuck the chess piece in. What's going to happen to the water? Oh my good gosh. Yeah, displacement, love that word. Rises, good. Great, great, great. You throw the chess piece in, it goes up. If it's gone from 50 to 70, what's the volume? By the way, don't be frightened to use an example to show the examiner you know. Even just to say, look, it might be like 50 and then it goes up to 70, then I would know that it's 20. Like if it's just an open question, you can use that. Yeah, so volume is amount of water, which I can't spell, water displaced. So that would be 20 centimeter cubed. Brilliant. And now you use the equation. You've got the mass over that. Now, if you're using the Eureka can, let's say they're sneaky and they say you can't use a measuring cylinder. Well, if you can't use a measuring cylinder, the Eureka can won't work. All the Eureka can is, I don't know if you can see this because this might be off of my screen. No, it's not. Right, all the Eureka can is, it has a spout like that. This is the Eureka can. You're going to fill the water just below the spout like that inside the Eureka can. You then get a measuring cylinder anyway. And you position your measuring cylinder under the spout. And with this one, you're not working out the difference. You drop your chess piece in. The water displaces and trickles in to your measuring cylinder, and you just read the number straight off. So that's called a Eureka can. It has a spout. I've got a Eureka can somewhere anyway. Oh, I'm not going to look for it now. Yeah. So, yeah, easy peasy marks, guys. Yeah, that's it, easy peasy marks. Listen, there's a real difficult version of this. They could ask you, a confusing version. They could ask you, how do you find the density of like vegetable oil? So a liquid. So the hard bit with that is you've just got to explain the nuance of, here's my vegetable oil. I want to measure the mass, but I don't want the mass of the beaker or whatever it is that it's holding it. So, yeah, the liquid one. So you just need to say, you need to say weigh the beaker without the vegetable oil, add the vegetable oil, measure the mass again on the balance, and subtract the container to get the mass of the vegetable oil. Or you can just say zero it with the beaker, put the beaker on the balance and zero, then add the oil. So you just need to explain that bit, how you're going to find the mass of the oil. Okay, then you can say add it to the measuring cylinder and you can measure the volume, and you can say repeat. And yeah, and with this one you probably want to repeat as well, repeat the measurements, that type of thing. So cool. Yeah, that's it, nice and easy. It's not that hard actually. It's not that hard. Okay, what someone said, did someone say specific heat capacity? Oh guys, the other one is, you could be all prepared for this mentally in your head, and they might give you a symmetrical object. So it's just width times height times depth to find the volume. They may give you some sort of cube or something, so you can do that as well. And you may have to convert them between millimeters. If it's like millimeters, you might have to convert between centimeter cubed or millimeters cubed to centimeters, and that type of thing. And just check your units, because you can represent density in kilograms per centimeter, grams per centimeter, kilograms per meter, as long as you convert correctly. Right, specific heat capacity. Let's zing to this. Okay, so really and truly, if they don't give you the electricity practical, then it's going to have to be this or density. That's the beauty of P1. There isn't a lot of options. So there's nothing in the alpha, beta, gamma. There's no core practical in alpha, beta, gamma in radiation. So you've only really got the density practical and the other one, and the this one. Right, specific heat capacity. This one is vegetable oil, so yeah. This one is saying for vegetable oil, that's nice and easy. For every centimeter, you can say it's a gram. So if you have 100 centimeters, you can say that's 100 grams. But more accurately than that, you do the same thing we talked about before. You just measure, just subtract the beaker from your mass measurement. Measure the beaker first, then add the oil, then subtract it. Now you have the mass of the oil, and you're going to use the equation. Q is energy. It depends which exam board, whether you're doing physics or chemistry, they change the symbols. I think in AQA they might even use theta as change in temperature, and in other exam boards they use delta, the triangle, for change in temperature. So they're just being a pain in the backside, but it's the same thing. Energy is mass times the specific heat capacity times the change in temperature. So all you need to find out is you have an electric heater. You're going to heat the oil, but use a joule meter to measure the energy and a thermometer to measure the temperature. Easy peasy, right? Joule meter measures the energy. Thermometer measures the change in temperature, start and finish. So you measure the start temperature before you switch the heater on. Then you switch the heater on and leave it for like 2 minutes, 5 minutes, 10 minutes. It's up to you. You then measure the change in the temperature, and you record from the joule meter the amount of energy transferred, and then you rearrange the equation, which is going to get you a mark. So if you want to find specific heat capacity, it's going to be like Q over mass times change in temperature. So you're going to get a mark for rearranging the equation, a mark for saying record the initial and final temperature, a mark for saying how you're going to weigh the liquid, and that type of thing. Okay. Okay, so you saw a practical specific heat capacity with an object. Also, what about using an immersion heater? Yeah, I mean, you could use an immersion heater. Listen, they can do it with an iron block or aluminium block. You stick the thermometer inside. You can drill a hole in it. Not that you're going to say that in your practical, but you can stick a thermometer in there and connect it up to a heater and a joule meter. Now the heater and then your joule meter, which is measuring the energy transferred. And that's all you need, the temperature change, the amount of energy, and then you measure the mass separately. There is one slight difficulty. Okay. Oops. Okay, one slight difficulty. What if there's no joule meter? They've never asked this, But what if they don't let you use a joule meter? Well, in the CGP book, they do some long-winded method where you've got your iron block, you connect it to your heater. That's going to make the iron block hot. You're going to use your thermometer to measure the temperature. But if you didn't have a joule meter, you would need an ammeter, and you could have a voltmeter. Now, you don't have to draw it all out, but you could have a voltmeter, probably connected wherever. And you can do power is current times voltage. Now, this is in the CGP, but it's never actually come up, this version of doing it without the joule meter. So how would you calculate energy transferred? Well, first you calculate power, you record the current and the voltage, and you do it over a time. You'd also time it for, like, say 60 seconds. And once you can work out the power by doing current times voltage, you can then do energy equals power times time. So once you've got the power, you can work out the energy that way. So just watch out for that. Very unlikely to come up, but there you go. Yeah. So what we got? Someone wants the plug. We got someone wants fission and fusion. They're in separate science. We can go through that. What else did people say? A Geiger meter. So it's called a Geiger counter, right? Claire said Geiger meter. It's called a Geiger counter. You can call it a Geiger-Müller tube. You can call it a GM tube. Now, the practical that can come up. Here are my radioactive P's, okay? They're giving out radiation. Someone could say to me, explain a practical how you could find out the radiation level of the P's. What could I do? Right. What you're going to do, get your Geiger counter. It's called a GM tube or Geiger counter, Geiger meter. It's Geiger-Müller were the people that invented it. So here's my P's. But first of all, I'm going to record background radiation. This is something I didn't mention before when talking about radiation. Record the background radiation. So don't bring my radioactive P's in the room. Sling them away. Don't bring them in the room. You want to record how much natural radiation from the sun, from the bricks in the building. There's natural radiation around you called background. When I say natural, that's the wrong word. There's background radiation from the bricks, from outer space, from food and things like that, and the rocks in the ground that we live on. So they're sources of background radiation. So let's say I got 20 becquerels of background radiation, or count rate. They sometimes call it count rate. Now I bring my P's in, and the radiation reading goes up to 300. How much were my radioactive P's? How much were my radioactive P's? So, anyone got an idea? How much would my radioactive P's be? Yeah, 280. 280. So, you recorded the background radiation first. So when you bring the P's in and the reading goes up to 300, you've got to take away the background radiation from the new reading to know that the P's are only 280. Yeah, so it's 280 rather than 320. So you just got to make sure you say record the background radiation first. And if you were doing this practical, you put in some safety things as well, like wear a lead apron, I don't know, don't use tongs to handle it, wear gloves, that type of stuff. So if they came out with that, that's what you'd have to do. What were we saying? Where were we? What were we on? People were asking questions, so we were on else did people say? Oh, someone said specific latent heat earlier. Let me just, and then someone mentioned the plug. Right, you also need to know this equation, which will be on your equation sheet. Okay, specific latent heat. Very easy to get this mixed up with specific heat capacity. And in a recent exam, I can't remember which one, but they gave a 6 marker at the end that was a calculation where they mixed the two up. So this is specific. Hopefully they won't do that again because that was disgusting. Specific latent heat. What you're really looking for in physics, 100% guaranteed to come up tomorrow, is where you have to use 2 equations from the equation sheet together for like 4 or 5 marks. If they give you 4 marks for an equation, or 5, definitely you need 2 equations. So they could do something like, here are the 2 equations, me being energy, it might say Q, but I'm using that, and then, I don't know, I'm putting delta T, that could be theta T. These 2 equations are linked. Look where they're linked. Energy and mass. This is the specific heat capacity. Now the specific heat capacity is the amount of energy required to raise 1 kilogram by 1 joule. Specific latent heat is different. That's the amount of energy to change state from solid to liquid or from liquid to gas. Now they could combine these 2 equations, okay? So what would happen if they combine these 2 equations, guys? What we'd do, they might say something like this. So substance X, of course they won't call it substance X, that's me just being a twit. Substance X has a latent heat of, I don't know, 100 joules per kilogram, right? So substance X has a specific latent heat of 100 joules per kilogram. What else? 2,000 joules are transferred. Let's make that 20,000 joules are transferred when it changes from solid to liquid in melting. Okay, so when it was melted, it took 2,000 joules to melt it. 20,000 joules, jeez, are transferred. Then what we want to say is the temperature increased by 15 degrees, and then we're going to say, this came up a couple of years ago, so hopefully it won't come up again. Find the specific heat capacity. So how would you do that? Anyone? See if you can do that, or if you can work out any of that. That's a disgusting 6 marker. Yeah, you'll get these formulas on the sheet. You'll get them on the sheet. And sometimes they will even give you them in the question. But you've got to spot the links. You'll have a 4 or 5 marker 100% tomorrow where you've got to use 2. Most likely in electricity, you'll have to use V equals IR, combine it with P equals IV, or Q equals I times T. So you'll have to combine 2. So for instance here, you got to look at what your common things are. So I would be going, okay, once I've got the equations, I'll be saying, okay, this is 20,000, and I'll be like, oh, sugar, Ray Leonard. To be honest, they probably ask you how much energy is transferred when it boils or whatever, but you could combine them. I'm not going to do it anyway. Yeah. Let's allow this. This probably isn't going to come up, but yeah, you go. The specific latent heat is 100 I don't think you can actually find it out because I've said when it transfers from solid to liquid. I haven't given you the energy transfer when 1 kilogram is raised. So I've said find the specific heat capacity, but you don't have all the information to do that because this energy would be different. Let's say this energy is 1000 joules. Okay, I'm going to say that energy is 1000 joules. But what I need to do is I need to do this first one to find the mass. These two energies are slightly different. The top energy here is the energy. This is the energy required to change from liquid to solid. This is the energy required to raise the temperature by 1 degree. So, but I can find the mass of the object here by going 20,000 divided by 100. So it's 200 kilograms, right? It's 200 kilos or whatever it is. I can take that down here, and I now know the mass is 200 kilos, and with that I can go 1000 equals 200 kilos. We don't know what the specific heat capacity is, and we know that's 15, and I could rearrange that now. Okay, and you'd rearrange that by doing we want to find C, so we do like E over M delta T equals C, whatever that is. 1000 divided by 200 times 15. That's going to be a really small number. All right, let's sing on. Okay, let's not spend too long on that. Let's clear that. We already did National Grid. What was there? Any other suggestions? Anybody else wanted to go for anything? Sophie made a good point. Yeah, there's something called specific latent heat of fusion. That is just specific latent heat when you melt a solid, and then there's specific latent heat of vaporization. They are exactly the same equation. E equals m times L. Exactly the same, but one is just for solid to liquid, that's fusion, and the other one we call specific latent heat of vaporization is going from liquid to gas. But yeah, any other things people wanted to go through? Yeah, so convection, let's have a little look at, someone said plug. Someone's been saying plug for a while. So plug, you've got a fuse. Oh my gosh, I haven't got the right colors to do the plug. There's some cheap ass thing here. Okay, all you need to know for the plug, you got a brown wire. Can't believe they don't have brown on here, but they don't. So brown wire is called the live wire. You can think of the brown wire, if you touch it you're going to poo yourself because it's scary. It's 230 volts of electricity potential difference going through it. You then have a blue wire that completes the circuit. This takes the electricity back to the power station, and this is known as the neutral wire. Okay, so blue wire, it's at 0 volts. Okay, and then we have a green and yellow wire running up the middle to the top of your plug. That's that bit of your plug that sticks out like that. That's the green and yellow wire, and that is known as the earth wire. Okay, and that is also at 0 voltage. So both the earth wire and blue wire, when working correctly, are at 0 voltage. Brown wire is 230 volts. We need a potential difference between the brown and the blue wire, otherwise we won't get any current flowing, because it's like electrical diffusion or electrical pressure. The push is coming from the brown wire around to the blue wire and back. You need to know the earth wire, this one, is connected to the metal case. So the earth wire is always connected to a metal case. right, on your appliance. So on your fridge, the outside of your fridge is metal, it'll have an earth wire connected to it into the plug socket. If it should become live, if the case becomes live, what that means is if the 230 volts start flowing through the metal case, or current starts flowing through the metal case, the earth will protect you. It will stop you getting an electric shock. How does the earth stop you getting an electric shock? It has low resistance, it has 0 volts, so the current will go through that instead of you, and it will go outside of your house and into the earth. That's why it's called the earth wire. The current will go out of your house and into the earth. Okay. You also need to know that the fuse, this by the way is a fuse, the fuse will melt when there's a high current, so that will also protect you. So we've got the fuse and the earth wire to protect you. The earth wire is connected to a metal case. If the case becomes live in the case of a short circuit and you touch it, instead of you getting the electric shock, the electricity, the current will flow through the earth wire. We've got to use the right words. Can't say electricity. The current will flow through the earth wire into the earth rather than through the user. So it will protect you from electric shock. You don't need an earth wire if the case is plastic. If you've got a plastic hairdryer, it doesn't need an earth wire because you can't get an electric shock off plastic. It's an insulator. We say it's double insulated. Right. The other thing that somebody said, what else did somebody say? I think somebody said, yeah, the fuse breaks the circuit. So when the fuse melts, the circuit becomes incomplete and the current can't flow. Okay, convection. Right, convection is transfer in a fluid. So let's quickly whack out, let's get convection done. So we got the heat. So you've got a heat source. This could be in your kettle. The bottom of your kettle is a little metal wire. That's an electrical immersion heater, okay? And it's also in your boiler that heats up the water in your radiators that keep your house nice and warm. Or when you turn the kettle on, why does the water get hot? And the reason is the water particles close to the heat source, they're gonna gain kinetic energy. So they're going to spread apart. You can rewatch this because I'm not going to write it down because I just want to smash through. So particles of the substance, whether it's water, whether it's air, whatever substance it is, particles of that substance will gain kinetic energy in their kinetic energy store. They will move further apart and become less dense. They will rise up and they will push down more dense. They will displace or push down more dense, colder particles of the substance back to the heat source, and then it will happen again, and we call this a convection current. So particles spread out, they gain kinetic energy, they go further apart, their density decreases less than that of the air or the substance they're in, like liquid. They then rise to the top of the container, they push down colder, more dense substances, and they go to the heat source, and the same happens again, and it goes round and round until the whole of your room is nice and hot. And that's convection. It's how heat travels through a fluid, and that's a fluid counts as a gas or liquid. So fluids are not just water, they're gases, or liquids are called fluids, right? Now, conduction is different. Conduction is through a solid, and conduction is how heat transfers through solids. If you can't remember that, think of the D in conduction. So conduction has a D in it, and so does the word solid. So solid as a D. Conduction is how heat transfers through solids. What happens is the first particle to get heated by the heat source gains kinetic energy, vibrates more, and passes the energy on to its neighbor, the next particle next to it. This then vibrates more, passing it on to its neighbor, and so forth. So conduction happens through solids. It's going to happen better through metals. What is it that metals have that will also transfer the energy through and have more collisions? Anyone know what metals have? Definition of convection is the transfer of heat through gases and liquids. Yeah, well done, Hatim. Yeah, solids, metals have delocalized electrons, so they make better conductors. If you've ever left a spoon in a pan of boiling water or something and then touch the spoon, you're going to burn your hand. They conduct heat because of the delocalized electrons, mean more collisions and more energy is passed on. They can conduct the heat better. But other solids will get hot as well. So, yeah. That's heat through a solid. Now, something else you need to know. The walls of your house, the thicker the wall, this could come up by the way, the thicker the wall of your house, the harder it is, or the more time it will take for heat to escape, the lower the rate of heat transfer. Some people get a foam called insulating foam, and this has come up in exam questions before. They spray foam like polyurethane, some sort of plastic foam, into the gap in the walls in their house, and this decreases the rate of heat transfer because it makes the wall thicker. And so we say it decreases the rate of heat transfer the thicker the wall. You need to know that. You need to know about radiation. Radiation can travel through a vacuum. Color black absorbs heat and emits it better. So if they ask you why do solar panels, why are they painted black, it's so they can absorb heat. That's the idea behind a solar panel, to absorb heat. If they ask you why is the inside of an oven painted black, that's a different answer. Or if they say why is your frying pan painted black, that's a different answer. That's because the color black emits heat, gives it out more, so it's going to pass it out into the food quicker at a higher rate, and it's passing the heat out by radiation. What else? White and silver colors reflect radiation. We're talking about heat. Heat is a type of radiation. Sound is radiation as well. What else do you guys need to know? Just trying to think. Your microwave's white on the outside, but it's really what the inside is. So what's the color of your microwave inside is what you want to look at. White on the outside don't matter. Yeah, so there's a big difference between reflection and emitting radiation. So reflection, the radiation bounces off of the surface and never goes in and doesn't heat it up. So if you wear a nice white t-shirt, don't know why I'm grabbing this, it's not white, but if you wear a white t-shirt on a hot day like today, you wouldn't have got hot because the radiation from the sun will bounce off of your t-shirt and not heat you up. If you wear a black t-shirt, the radiation will go into the t-shirt and be chucked back out. So it will feel hot because it's being chucked back out, but it's going to make you hot as well. So yeah, we want to paint things black when we want them to suck in heat, but we want to paint them black when we want them to chuck out heat. So if you painted your radiators black, they're going to chuck out more heat than being white, but people tend to like to paint them white because it looks nice. Yeah. Yeah, but we say absorbs. We don't say sucks in. We say black absorbs heat. Black and matte, so not shiny, absorbs. Shiny, light colors like silver and white, they reflect heat. Okay. So you just got to adapt your answers to what they're asking. So if they say, why is this black? And you think, oh, it needs to take heat in, then you say, because black is a good absorber of heat. If it says, why is this black? And you're thinking, right, that needs to get heat out to cook food or something, then you'll say it's because black is a great emitter of heat. Right, yeah, there's an air gap between windows, that's right. And that air gap, what conduction, So there's three ways heat can travel: conduction, convection, and radiation. The air gap ain't stopping radiation. Radiation can go across outer space, thank God, otherwise we wouldn't get heat from the sun and we'd all be frozen. But the air gap stops the conduction of heat. So the air gap prevents conduction. Air is a poor conductor. It's not impossible, but it's got to wait for a while for one air particle to come together to pass the heat on by conduction. So it's a very poor conductor. In fact, it's an insulator. So that's why we have an air gap in windows, and why there's an air gap between the walls of a house. Right. Someone said they wanted to go through static electricity. I'm getting a bit tired now. I'm going to finish in a minute. So static electricity. Oh, jeez. What have you guys got to know for static? I just got to quickly check what you got to know for static. What's my bloody AQA book? So, what have you got to know? Static's quite an easy topic. So, essentially, every single thing in the world is made up of positive and negative particles. Yes, we call them protons and electrons, but when you're talking about static electricity, you can just call them negative charge or positive charge. Okay? When you rub things together, the negative charge can move, positive charge can't move. So, for instance, you could have a slide, you could have somebody going down the slide, right? When they rub along the slide, depending on whether the slide is plastic or metal or what, negative charge can move from one object to another, and then that person can become charged. Now, you can be charged if you're positive, you can be charged if you're negative. So this is just a tiny bit of triple, but yeah, basically when you rub two objects together, negative charge can move from one object onto another. And if the object is an insulator, the charge gets trapped. So if the object is plastic, the negative charge on the plastic gets trapped, and then you can get a spark and you can get some dangerous things. So you can earth things to prevent that as well. Now, let's just have a quick look. Yeah, fission and fusion are also triple. I'm happy to go through that if everyone on combined is done. So yeah, you just need to know you can have a rod here, right? And this is got 3 positives, 3 negatives. You can rub that with another rod. Say this rod's got 2 positives and 2 negatives. After you've rubbed it, only the negative charge can move. So let's say, now depending on the material, the positive charges can't move, and that's essentially because positive charge is locked inside the nucleus. But now this has got 5 negatives and 2 positives. So we would say the rod in this situation has become negatively charged, and the cloth is positively charged. And positive and negative charge, they attract to each other. So you can also get sparks. So now if you held that rod near someone as they walk past, their body has positive charges in it, the spark of negative charge could jump out the rod into someone and give them a shock. More than likely, the negative charge will just go straight through their legs into the ground and be earthed, unless of course they're wearing plastic shoes where the charge stays in their body. And that's why when you touch someone, sometimes you touch your mum or your dad, or you touch a friend at school on the arm and you get a little shock and you go, ooh, you're wearing plastic in your shoes, and the charge they've rubbed against something and got negative charge in them, and it's stuck in them. It can't get out into the ground, it can't be earthed, and so when they touch someone else, it goes through them and into the earth, and you feel a spark. Yeah, I did the plug roughly. How would you know if it's negatively charged, the rod, or positively charged without seeing these particles? Well, you could get another rod that you know is negatively charged and hold your rod to it. And if they push away from each other, they have the same charge. So we could electrically charge a rod and make it negative, and we could then hold it to the unknown charge. And if they push away, they've both got the same charge, so they'd both be negative. And if they attract, then we would know that one is negative, one is positive. So you'd need to know the charge of one to know exactly whether it was positive or negative. You couldn't tell because both positive charges can repel and two negative charges can repel. So you'd need to know the charge on one to be able to find out the charge on the other. Yeah, now there's another thing that's just a little bit, it's quite easy, but they talk about charged particles have electric fields around them. And all this means is they say that they put a Q for charge, coulombs, put a Q there. And they just say that if you've got a positive charge, we draw arrows at right angles around here. And just draw arrows all around. And then with negative charge, we draw arrows like this, and these arrows represent the electric field. So these are like field lines like you get with north to south on a magnet. So we're kind of saying if you do magnets in paper 2, that the north pole of a magnet, the field lines always run to the south pole. It's kind of the same with electric charge. They say the field lines always run from positive to negative. So if you have a negatively charged object and a positively charged object, you get lines of force, electrical force, coming out of the positively charged object and heading towards the negatively charged one. Okay. And if you put these two objects together, they experience a force, and that's really it, really, for charges. My bedtime was about like 8 o'clock. I got kids, so normally I get to bed nice and early, really. Well, I don't actually. I get about 5 hours sleep a night. So, what else? What else? What else? Just having a flick. Okay, one more on the triple, and then just on the triple, because there's some combined people who might be like, what? So just one more on the triple. If you're doing nuclear fission, you just need to know that you got neutrons smash into a large nucleus, okay? And when they smash into a nucleus, what happens, guys? 3 things come out. Anyone know what the 3 things are that come out? Okay, anyone know what comes out of the nucleus when a neutron collides with it? Any triples? Triple peeps? Anyone doing triple? I'm only going to take 2 seconds over this, because does anyone want to do nuclear fusion? Or are you guys all doing combined, because then I'll just louder nuclear fusion? Because if there's no one who's really doing the triple, then we can louder nuclear fusion. You get daughter nuclei. They used to call them daughter nuclei. You can just call them small nuclei if you like. So you get 2 smaller nuclei. Okay. Oh God. And then you get neutrons. Normally 2 or 3. I'm drawing 3. And you get kinetic energy. So if you're asked for 3 marks, what is nuclear fission, the answer is it's when a neutron splits a large nucleus into 2 small nuclei, more neutrons, and kinetic energy. The kinetic energy is found inside the neutrons. They're moving. Now, that's nuclear fission. What happens? They might ask you, why is it explain why nuclear fission is a chain reaction. What happens to these neutrons? Does anyone know what these neutrons do? Anyone know what these neutrons do? They go on and hit another big up nucleus. Okay? And the process repeats again. But this time there's 3 neutrons, so 3 nuclei split, and we release 9 neutrons, 3 from each. And then those 9 neutrons go on and split 9 more big nuclei and release 27 neutrons. You see, you're tripling it. And then those 27 neutrons go on and split 27 big nuclei, not nucleuses, and they release 81 neutrons. So you see, within a second, that's what we get when we get a nuclear bomb, when we get a nuclear explosion. Within a second, trillions and trillions of nuclei have exploded. Well, that's what happens if you have uncontrolled fission. So nuclear fission is great for making energy. We can use this to create electricity. In France, for instance, they get like 60-70% of their electricity from their nuclear power stations. So they sell most of it to us. So most of the electricity coming into your home right now is produced in France. Yeah, it's a really good system. Of course, there's radioactive waste. There's a bit of a downside to nuclear fission. Fuse, yeah, so that's nuclear fission. Oh, watch out for, there's some dirty nuclear fission equations, and they look like this. Okay, so watch out for this. You can have a neutron, 1, 0. Going to smash it into my nucleus X. And my nucleus X has got a mass of 235 and 92. And then this is going to become 2 daughter nuclei, right? And this is going to, which plus, I don't think any of you are clever enough to work this one out. Okay, guys, what are my missing numbers? What are the missing numbers? This is a nuclear fission equation. Okay. Sorry. So what you're looking at here don't forget, guys, the mass number, and this is where people make a mistake. You've got to include the mass of the neutron. This neutron smashes into atom X, and for a second it's combined the mass numbers to 2, 3, 6. We don't have to worry about the bottom number, that's still 92. So what about over here? Don't forget this cheeky little 3 neutrons. They have a mass of 3. So don't forget that I have to make all of this, the 3 neutrons, the 70 here, and the mystery one have got to add up to 2, 3, 6. Because mass, of course, is conserved. It's the same before and after. So really, I got 73 there. I need to do 236 minus 73, and that's going to give me the mass number. So 236 minus 73 is, I need my calculator because my mental maths at this time of night is not going to be good. So 163. And that, I just take that from that, and it's going to be 60. Okay, so watch out for that, guys. Yeah, 163, and at the bottom it's going to be 60, which is easy because neutrons, they ain't got no number at the bottom, they just got mass. So watch out for these multipliers when they have 3 neutrons, if they give you a nuclear fission equation tomorrow. Watch out for that. Very quickly, I'm going to do fusion. So fusion is like where you have 2 smaller nuclei, like deuterium, which is an isotope of hydrogen. Now, I don't believe, let me just check, because depending on the exam board you study, because actually at GCSE what we're learning are models, and those models aren't perfect. So depending on the exam board you study, you might have to know it loses mass or not. Nah, you don't, so that's all right. That's okay. So what would happen if these two atoms combine on AQA? It will form helium with the numbers 4 and 2. This happens in the sun, and this is nuclear fusion. So what we just say is two smaller nuclei combined fuse to make a larger nuclei. But here's the key. They release trillions and trillions times more energy than nuclear fission. So the most energy, the best system we have for creating energy on the Earth is nuclear fission. It makes lots of energy, the one we just looked at before. Nuclear fusion blows that out of the water. You think about the sun, every energy of every human being, every plant, all of the energy on the planet comes from the sun. So that's the kind of level of energy you get when you can do nuclear fusion. We can't do that at the moment. The Chinese are working on it. They're building some big machine. The Americans are in a race to do it. Everyone wants to do viable nuclear fusion. We can actually do nuclear fusion, but it costs you like $200 million to do it for 8 seconds. So why would you want to do it? Have you got a spare 200 million to just burn in 8 seconds and get nothing for it? So doing experiments on nuclear fusion is very difficult. Why does it cost so much money? You need to know that, yeah, nuclear fusion is happening in stars. It's happening in stars, but we're trying to do it on Earth. And what we do is, the problem is a star is already, the core of a star is already millions of degrees of heat and incredible pressure. And it's enough to smash together 2 hydrogen to make helium and release tons of energy. But we're trying to do that ourselves, because if we can do nuclear fusion, then we can have free energy and we can go and explore the universe and do whatever we want. We can create anything out of anything. Basically, it'll give you like almost divine like power. So that's why everybody's after being able to do nuclear fusion. You have to know that it's very difficult to do nuclear fusion because you require temperatures of hundreds of millions of degrees. So that's one of the downsides. You also need incredibly high pressures to force the atoms together. At the moment, this can only be done inside the core of a star. We can do it on the Earth, but it just costs us so much money. We don't get anything out of it. Yeah, that's right. Yeah, it happens in stars. We can actually do it on the Earth every year, like the Chinese do it for slightly longer, then the Americans do it for slightly longer. So it's kind of like competition at the moment to try and India's probably doing it as well. Competition to try and get nuclear fusion done, and but we can do nuclear fusion, but at the moment it's not viable. We don't release as much energy as we put in. And that's rubbish, isn't it? Like, it's like you spending £200 million and only getting £1 million out. Less than that, you're only getting £100 of energy out. So you're like, oh, I just spent £200 million and made £100. So at the moment, it's not good. We want to get it to the point where we put £100 in and we get £200 million of energy out. That's basically what we want. So that's nuclear fusion. Small nuclei fusing to become a large nuclei. Right, I'm off to bed. Good luck. Take care, and I'll be doing some lives over half term. I'm going to do a few lives next week. And then obviously on the night before the exams, I'm going to do lives. But I'm going to do some next week as well. So yeah, good luck with your exam. Stay calm. Remember, if you get a 5-mark calculation question, you're probably looking at using 2 equations. So you need to locate the equations. Use a highlighter pen, circle the units and the numbers in your equations. Okay. Yeah, and enjoy your half term. But make sure you revise. Remember, so far in your life, if you're studying GCSE at the moment, so far in your whole life, your biggest holiday has been 6 weeks. So you've never had a holiday bigger than 6 weeks. And by the end of the 6-week summer holiday, you generally have even forgotten what school looks like, what it's all about. You can't even remember really being in lesson after 6 weeks. This is going to be 50% longer. You're going to have 9 to 10 weeks of holiday. So when you see the sun shining now and you're thinking, oh, I just want to get out and chill, I don't want to revise, you need to be revising, because you're going to get 10 weeks of sunshine, chilling, relaxing. And what you don't want to do is sit there for those 10 weeks and think, oh my God, I didn't work hard enough. Now, forget, you can't change what you've done the last 5 years, but you can change what you're going to do over the next 3 weeks and over half term. You can lock yourself away, not too hard, but study, study, study. Because no matter how bad your levels are, if you work hard over half term, you won't regret it. You'll, even if you've done bad, you'll think, you know what, I tried, I did my best. But if you go into those 10 weeks, 5 weeks in, and you're thinking, I'm going to fail all my GCSEs and I didn't do any work, it's not going to be good for your sense of self-worth. So do some work over half term. You'll feel a lot better for it regardless of what your levels are. All right, guys, take care. And yeah, see you later.